Hey everybody, this is Waehner from Confluent. Great to be at the InfluxDB conference today. I will talk about IoT architectures for a digital twin with Apache Kafka and InfluxDB. So this is really an exciting topic to build a digital replica of things, to build it open and scalable and reliable. So let's start with the talk. It will be around 40 minutes and I have a lot of topics to cover. So I will spend around 5 minutes on each of these topics here. I will introduce you to a digital twin and what that actually means, and then show you a few real-world examples. And then I will introduce you to Apache Kafka as more or less the de facto standard for an event streaming platform, not just in IoT, but in this case, of course, for building digital twins. So I also have to talk a little bit about other IoT platforms which complement Apache Kafka. And then I will talk about how to build a digital twin and different IoT architectures, where we then leverage Kafka and InfluxDB for that. And at the end, I will also talk about a demo which we already built and how that can look like with these kinds of technologies to build a really scalable real-time infrastructure for analytics. With this, let's begin with the first section, a digital twin and merging the physical and the digital world. What is it? First of all, let's talk a little bit about the motivation why everybody in IoT is talking about digital twins. This is a report from McKinsey, but in general, it's really getting realistic everywhere that people are going away from building just machines and manufacturing things. This worked for many, many years, but in the meantime, the machinery is not really where the margins come from. So you earn less and less money, and therefore more and more of the manufacturers and other companies do not just want to produce things, but also sell additional software and services, as you can see on the right side. So there's a clear trend here, and we see this in every industry. And this is really the main motivation. People are going away from just selling things, but also adding additional software and service on top of that. And with that, we come to the digital twin, which is in the end, merging the physical and the digital world. On the left side, you see a few of these things. This can be a car or a plane or a robot, but this can also be, for example, a human. Or this can even not be a thing at all, but something like a process which you want to digitalize. And on the right side, you see a few of these examples where you can leverage that for doing things like simulations and calculating the downtime reduction and doing inventory management, what-if simulations. There are so many different use cases where you want to build a replica of the existing thing to do calculations and predictions on that. So in one sentence, really a digital twin is a living model that drives a business outcome. And that's also important. It's really not just about technology, but really about getting business value out of a digital twin. And here's a few examples for use cases. The first one is how Siemens defines this. And here it's about building a digital twin for buildings. Actually, they call it, therefore, a building twin. And in this case, it's really a digital solution for the entire building life cycle. And that's true for digital twins very often. You're really starting from the design phase and then think about the construction and operations, which in case of a building can take 20, 30, 40, or 50 years. And then finally, you think about the demolition. And all of this can be planned and simulated and implemented with a digital twin much easier and more cost-effective and efficient. Another example is a connected car infrastructure. So this is, for example, what Audi is doing with Kafka and event streaming a lot. So they are ingesting all the data from the cars when they already exist and store this data in the cloud to process it in real time for analytics. For example, for after sales and for communicating with the customer. So they can use predictive behavior to do recommendations like, for example, working with partners and making recommendations when to go to a food stop. Or maybe do a recommendation when to go to the repair shop next because your engine might break. There's many other use cases in automotive scenarios like for predictive maintenance and also already in manufacturing where you build a digital twin for the cars before you even have built them. And this third example is about the humans. So in healthcare, you, for example, monitor the humans. This might be just in a hospital or really 24/7 when you are also living at home. And with this, you continuously monitor the sensor data, which is consumed from the human in the end somehow. And then you can do correlations on the data and do predictive calculations to send an alert out to a doctor or to the smartphone of the human to do something like going to a hospital before it's too late. So here the digital twin is also based on the human person. And I think this is a very interesting use case and very different from something like a car or a building. And what's also important when we talk about digital twins, this is almost always about implementing some kind of intelligence, which the buzzword is AI or machine learning. In the end, it's some algorithms under the hood which analyze historical data to find insights and then to apply this in real time to new events. And so machine learning really is a complementary concept for the digital twin. And it's really important to understand that this is also a continuous process. You learn from historical data, you deploy this model, but then you gather new information about the person, the car, or the building, and act again on that and retrain the model. And therefore, good data is really a key for success, not just for machine learning in general, but also for any digital twin. And with this background in mind, let's now talk a little bit more about the real world challenges of a digital twin, because it's not that easy to build it like I just talked about the stories on the pictures. And here's an example from the automation industry, which really depicts what some of the problems are. And here on the left side, you see a lot of the real world machines running in the factories and in the plants. And this is technologies which typically run there for 10, 20, 30, 40, 50 years. So on the left side, you see some Siemens examples, and they have PLCs which are running for 50 years. And maybe if you have even a modern PLC, it's still an A7, which might be 20 years old. And so this is very different from modern technologies like cloud solutions or big data solutions, which evolve quickly and you change them maybe after 5 years for something better. And this is the first challenge. So if you build digital twins, on the one side, you also have to integrate with legacy technologies. And on the other side, you have to plan accordingly, not just for the next 5 years, but really for the next 50 years. Often even also from compliance reasons or warranty reasons about your product or your service you offer. And this is a big challenge. And therefore, of course, there is this evolution of convergence between IT and industrial automation. So this is typically this IT and OT conversions people talk about. So on the one side, the software and information technology is changing, but still, even there, you still have this old stuff. Like every big company still has mainframes running, right? And on the other side, the same is true for industrial automation. In OT, you have very old systems and proprietary technologies. And also here you get more standards in like OPC UA, but still you have many different technologies and hardware to integrate. And so you have to somehow get this conversion done. And that's a big challenge today, but that's definitely the future of automation industry and also of many other industries. And so in summary about the challenges, it's in the end a combination of complexity, cost, and scalability. Complexity because there is a lot of proprietary code and often there is not really even an interface to all technologies which you want to integrate. And from a cost perspective then, of course, if you're going with a specific vendor, then the integration software is also coming from this vendor. And all this package is not really cheap and it's definitely not open and elastic and also not extensible. So you buy this from this vendor and integrate it with your other solutions. And on the other side also, it's typically a monolithic solution. So you cannot really scale this up easily or simply move this to the cloud to scale it up. In case of manufacturing, it's not in the cloud anyway, because many of the processing has to happen at the edge. And so it's a combination of hybrid scenarios. And so this is a lot of blockers which people see when building digital twins, because in many cases, you're not starting greenfield. And this is true for manufacturing and factories, but this is also true of healthcare, because rarely you can build a completely new hospital and start only with open and new technologies. And also often from a compliance reason, you still have to integrate with legacy standards and protocols, which are not there today for the future. So a lot of challenges to solve to building a digital twin. And on the other side with these challenges, I mean, there is more and more demand for doing things more flexible and more scalable and more agile. This is in the end what we're doing today in greenfield applications in the cloud, when we build new things with open source and cloud services. But this is not what the real world is. And that's really true for all these examples I brought up, like automotive or manufacturing, or also for healthcare and many other use cases. So there's huge demand for building a more open and flexible and scalable platform. And this is in the end what I want to talk about today in this talk, and also explain how this complements the existing world so that you can connect both to each other to add value to the use cases. And this is actually where now event streaming and Kafka come into play. So let's take a look at that. Apache Kafka is an event streaming platform, and actually it's really a de facto standard in the market. There's a few other frameworks out there, but in, I would say, 99% of use cases for event streaming, people choose Apache Kafka because it's established on the market, it's battle tested, and it simply works very well. And it's important to understand that Kafka is really much more than a messaging system. I hate when people say that because it's just a core of the product, but Kafka is much more. Even the core of Kafka is already messaging and storage, so that you decouple producers and consumers from each other. But Kafka is much more than that. Kafka is also an integration layer where you can integrate with existing databases and messaging systems, but also with modern technologies like a cloud service or like a time series database to do real-time analytics. That's what we will see today. But what's really important to understand in the beginning is that Kafka, as I said, is not a messaging system, but has very different characteristics. So the core of Kafka is a log. This means producer produce data and append it. This can be sensor data, but this can also be logs or mobile apps or any other information which is appended here. And then consumers can consume the data like they want to consume it. There might be a time series database which consumes data in real time for analytics, but another consumer completely decoupled from this might be a batch analytics platform like Hadoop, where you do some MapReduce, which takes hours to do something, or like training a model in batch mode. And then there might also be a third application, which maybe is a mobile app, where you only have some request response communication with Kafka with a REST API. So you're very flexible here, and Kafka decouples all of that because it's not just a messaging system to send data from A to B, but it's also a storage system. You can store the data in Kafka as long as you want. For some use cases, it's just some hours. For some others, it's months or years or even forever. Kafka was built for scale from the beginning. So it's now over 10 years old. And in the beginning, all the tech companies used it. So here's just a few of the examples. Today, of course, the situation has completely changed. And in the meantime, more or less every bigger company is using Kafka for many different projects. And what's the even more interesting fact here is the second one, that Kafka is not just used for big data. And that's what I really want to point out here. While people know that Kafka is a big data framework, because that's what it was built for in the beginning by LinkedIn, today, around 70% of the projects I see at our customers are not about big data. It's more about mission critical data and transactional data and important events to process. So it's not just about data at scale, but really processing data at real time in a critical manner without downtime and without data loss. And that's often why Kafka comes into play. And so let's take a look at a few examples here. And the point is not to walk you through all of these different use cases, but really just to show you there is many different use cases what people use Kafka for. Some build really their core platform around Kafka. And that's not just LinkedIn's and Netflix, right? They're newcomers, which are in the end here for 10 years and build everything in the cloud. For them, it's pretty easy to build everything from ground up in an event-based manner at scale with Kafka. But other traditional companies also do similar things. So we are, for example, working with a lot of banks, and not just new banks and fintechs, but really traditional banks, which completely re-engineer their core banking platform around Kafka. And this is really the most critical transactions they process. And there is many other examples, and people use it for building microservice architectures, for replacing existing middleware, for building faster transactional processing and fraud detection. So there's plenty of different use cases here. And therefore, the reasons why Kafka is used so much is really, it's a combination of different characteristics. In the past, there was already tools to process big data sets like ETL tools, right? And on the other side, messaging systems exist for 20 years for mission critical deployments. So both is already available, but what makes Kafka so different is that it's an open source framework which combines the power of big data ETL on the one side with real-time messaging on the other side. And this combination makes Kafka so powerful. And the fact that it also provides integration and processing capabilities, that makes it really such a powerful framework. And that's why it got the de facto standard for what I call here event streaming, the combination of messaging and storage and processing and integration of data. And as I said before, let's focus more on digital twins again and IoT projects. This is always relevant also for machine learning. And here we see more and more people using Kafka, not always for the whole platform, but for parts of it at least, for doing things like data ingestion and processing in real time at scale. But sometimes also for doing things like deploying a model in real time in a robust environment to do predictions in milliseconds, or also to build a real-time monitoring infrastructure for technical monitoring of everything, but also for business monitoring. Like if you have a use case for predictive maintenance, you want to process and monitor all of that in real time. And that's really where Kafka comes into play more and more in machine learning infrastructures. And also one more point to point out about Kafka is that it's not an IoT platform, and that's absolutely true. And therefore, Kafka is not an all-rounder like any other product, right? So it's combined with different other technologies. Kafka is not good in things like device management. There's no out-of-the-box solution for that. It's also not built for unreliable networks. That's where, for example, MQTT comes into play. And also, for example, if you want to connect on millions of devices, that's things where other technologies are much better at the edge. So it's really complementary. And therefore, with that, let's think about building a digital twin and how Kafka complements IoT platforms. So first of all, let's understand what IoT platforms are there in the market. And I can tell you there are many available in the market. Here's just a few of them, right? Today, probably over 1,000 IoT platforms are available. Some are for some niches, and some are really big platforms where you can do more or less everything with that if you want to. Of course, it comes with a complexity and cost with that. There's different kinds of platforms. There is commercial industrial IoT platforms, like here you see a few of the examples. These are specifically built to deploy them, for example, in a plant, to integrate with machines, with PLCs, often directly integrate with proprietary interfaces. Like if you're based in Germany and have a lot of Siemens machines, then probably Siemens MindSphere might be a good choice for you. And right, there's a lot of these platforms on the market. They all have their strengths, but they are often also only very good in what exactly they are built for and not for all the rest of the things. And of course, also the cloud providers have IoT offerings. So here's a few examples like Azure or all the other cloud providers. And actually, they are not just providing solutions in the cloud, like for device management or integrating with the rest of their analytics services. But in the meantime, they also provide some kind of capabilities at the edge, where you can deploy some of the services in the factory and then replicate data to the cloud. Again, this comes with trade-offs. So cloud providers focus on their cloud services, and that's where they are very strong. So integration and IoT capabilities, especially at the edge, are not really their strengths, but they provide some kind of features here. And then last but not least, of course, there is these open source frameworks and standard-based things. Like there is, as I mentioned before, MQTT, which is a standard built specifically for IoT, where you can work in unreliable networks and connect to millions of devices. And then you have implementations behind that, like in this case, -Q. And so there's different niches, and then there's different solutions with standards and with open source implementations there. So as you have seen, there's a lot of different frameworks and solutions for IoT on the market. And now let's think about how we can combine that, because in the end, it's a spoiled for choice. How do you build a digital twin? Before we talk about different options, let's understand the characteristics of a digital twin. So there's different things you need to think about. And the first one is connectivity, because typically you have to connect to many different things. Of course, the devices and machines, but also then to enterprise software, like the MES system and the ERP system, which are related to the IoT stuff. But also then, for example, to the CRM system and to analytics tools, which are more out of scope of the industrial IoT stuff. And often you want to even implement bidirectional communication between both. Homogenization is very important. So you often have different kind of technologies and even some proprietary stuff, especially if you go to industrial IoT. So you want to get some standardization and decoupling between that. And also, of course, reduce cost, because of course you can buy everything from one single vendor, but it might not be the best solution from a revenue perspective and from a TCO view. You need to be really flexible to change over time, because the future improves things and you need to add different technologies. And you also need to change existing things. So you need to have a reprogrammable and smart infrastructure. And with that, also you need to provide digital traces to diagnose problems. So of course you want to process everything in real time in a best case. But then when all these events happen, then you also want to consume old events and analyze them over time. And with that, the final characteristic, which is important for digital twin, is the modularity. So you need to tweak the modules of models and machines. There's many different problems and use cases, and there is not one single all-rounder which can implement all of that. So even if you're talking about one digital twin, this can be many different things. There might also be one digital twin for each device, and then a bigger digital twin for a factory. And then maybe a digital twin for each country or region. So there's many different kinds of digital twins which you have to think about. And with that, let's now think about different scenarios how you could do that. A digital twin can be a monolith, of course. So if you have a specific IoT platform like the ones we've seen before, you can do the digital twin just with that. If it works for you, that's totally fine. But if you think about these characteristics in the top right, like being more standard-based and open and flexible, and decouple the things in own modules, then you typically separate things regarding your concerns and use cases. And so another example might be here that you build your digital twin actually in a database like in InfluxDB, where you do your real-time analytics and ingest the data into it from the IoT platform. This is already a more flexible solution, but still in the end, it's just built for one problem then. And really actually what we see often in the real world is now this picture here, where you combine event streaming with Kafka for building the connectivity to the IoT platform, or even directly to the MQTT interfaces. And on the other side, of course, you ingest the data into a database like InfluxDB for building a digital twin and for storing the data long-term and doing analytics there, but also consuming it from other applications. And this is actually where Kafka comes into play, as I introduced it before. The strength of Kafka is not just in ingesting high volumes of data from one interface to the other, but the strength is really also that it decouples the different systems. And so while one interface might be the digital twin, in this case we use InfluxDB and ingest the data in real time, there might be other consumers from the data, and some might also be real time, but others might be a batch application. So in addition to doing the real-time analytics with InfluxDB, you might also do some long-running MapReduce jobs in Hadoop, or create some reports there, or train some analytic models with Spark. That's all totally valid. And this is exactly where Kafka comes into play, because with this, the core is real-time with Kafka, but you still store the data there. And therefore you can also connect with other systems which consume the data in batch, or maybe from a mobile app with request response only when you want to get some data out of that. And therefore you see here, if we think about these characteristics, this is really getting modular and decoupled from each other. But still, you have these digital traces in Kafka in the middle, where you store everything event-based in guaranteed order with timestamps. And so you can either just put it from the source to the sink in real time, or you can reconsume the data again and again. So here you're very flexible and connect to all the different systems in a standard-based manner. And then another option we also see from time to time is that you still want to get all these characteristics being decoupled and modular and connect to everything, But actually, instead of using another IoT platform to connect to machines or devices, you directly connect to that from Kafka. And that can be done with something like Kafka Connect and connectors for MQTT, or maybe with a framework like PLC4X and its Kafka connector to even directly connect to PLCs like Siemens S7 or Modbus or BACnet or all of these. And so there's many different architectural options, and also there is trade-offs and no best option for that, right? But with this solution, you also have this decoupling and modularity, but you directly integrate with the data generators for the digital twin data. And so there is no best solution. It's really different options you need to understand to make the right choice for your project. So with this understanding now, let's talk about different IoT architectures, because it really depends on the use case, how you want to deploy such a solution with Kafka and InfluxDB. First of all, why do we see people combining Kafka and InfluxDB for building a digital twin? So this is in the end a very common architecture we see in many, many companies. So as I said before, Kafka is used often for building a pipeline, of course, high throughput, low latency at scale, but also for processing the data with Kafka native technologies like Kafka Streams or KSQLDB. And it also is the back pressure and decoupling between the sensors and between the consuming systems. Sometimes some of these systems fall behind and you need this back pressure. Or sometimes you want to keep it in Kafka because in addition to a real-time ingestion, another system wants to consume it in batch, like an Hadoop system, for example. And so you combine the advantages of Kafka with InfluxDB, where you keep it in long-term storage for doing both batch and real-time analytics based on the time series data. And then you can, of course, create also dashboards on that or other things which InfluxDB and the ecosystem features you. So in summary, the combination of this allows to build an open and scalable and mission-critical platform. And I think that's really critical in most digital twin scenarios, because this really has to run 24/7 without downtime and without data loss to really create the added value for your business case. And with that, in the end, there's then different architecture options. Sometimes we see this deployed directly at the edge, for example, in a factory. If you want to do processing in real time at scale in a factory and then also do some analytics there, then you should really deploy it there. This has low latency and this is very robust. And it's not a good idea then to replicate or ingest everything into the cloud first. This is low latency. And should it be, but it's not. And also the cost is very big. So all the data which is produced by sensors can get very expensive. So often either you do just edge computing or you do just some filtering at the edge and some processing and then send the process data to the cloud to do something there. But you can really also directly build a digital twin at the edge with something like InfluxDB. It simply depends on the use case. And then, of course, in some other use cases, you want to build a centralized digital twin. This means that you have either also Kafka at the edge and do some filtering and processing, but then replicate the data from different factories in this example to one central Kafka cluster in the cloud or in a big data center. And then you aggregate and process it there. It's like you ingest it all into InfluxDB coming from several different regions or plants so that you can correlate the data from different regions or plants. And sometimes in some different plants, you might even use different technologies like you see in the top left. Here we are using an open source ecosystem at the edge, like integrating to the machines and devices with Kafka. At the bottom left, you see, this is maybe a plant in Germany and there's a lot of Siemens machines. So here Siemens MindSphere might be the best solution. This can also be used at the edge and then replicating data into Kafka Cloud with Siemens MindSphere's Kafka connector. All of these platforms have Kafka connectors for a good reason, right? And then you can aggregate and correlate this data with a digital twin in InfluxDB to process data in real time and store it there, to create dashboards which compare, for example, the different values between the different regions. And then, of course, if you are a big company or global, then in the end, you want to get information about your global infrastructure. And there is many different architectural options here. So on the left side in yellow, you see one example where we deployed one multi-region cluster. This is an option from Confluent for Kafka, where we provide really to stretch a single Kafka cluster over different regions. So this is meant for high availability and disaster recovery with zero downtime and zero data loss. So this can really handle even the disaster case that a complete data center or a complete cloud region is down. And still you have zero downtime and zero data loss. So this is the most powerful option. However, of course, it's a little bit harder to operate and to deploy that regarding networks and so on. And therefore, there's other options like linking clusters together and replicating data between two Kafka clusters in real time, like between the left yellow one and the blue one in the middle. So this is one other option. So, and at the bottom in yellow, you see this aggregation cluster where maybe in one country you have different plans and they do some edge analytics, but you also replicate it all to one central Kafka cluster to do the analytics there, maybe with the time series analytics and in parallel with machine learning and so on. So there are several different options. And in the real world, what we see for global deployments is that it's not always the same technology, right? So you might use AWS in the US and in Europe, but then in China, there is no AWS or Europe. So you run, for example, on Alibaba Cloud or in a private data center. Some of your teams in Japan might decide to use Kubernetes for all the infrastructure. So you deploy Confluent and InfluxDB there on Kubernetes, maybe with the Confluent operator for Kafka. So that doesn't really matter. And often over time, this changes a lot because technologies change and evolve. But here you are very flexible and can deploy this in the way you need, at the edge, in the cloud, or in hybrid scenarios. And this is really how we see people building digital twins over time. And this architecture evolves. This is not a big bang. You start, for example, in one factory and with one cloud deployment and then roll it out all over the world for your different plants or hospitals or connected car infrastructure or whatever the use case is. And so with this understanding, now let's talk at a specific example. So this is in the end what we have built on GitHub to show how easy it is to implement an infrastructure for real-time analytics and processing at scale. And to start this use case from the left, so we have built really a scalable demo where we connect to 100,000 cars with an MQTT proxy. And this data is ingested in real time into Kafka, where we then process the data with KSQL on the top left. And then also we use some other cutting edge technologies. In this case, we use TensorFlow to train an analytic model where we directly consume the data from a Kafka cluster. So we don't even use a data lake in the middle like Hadoop or S3. And then we deploy this model to the right into a real-time analytics platform, like a Java application, or maybe even just a Python app running on Kubernetes. And then parallel to that, we also ingest the data into InfluxDB, where we build our long-term storage for the digital twin. Because the other stuff is real-time processing of data, but then we also want a long-term storage and leverage the features of the time series database so that we can do analytics both in real-time and in batch there. And also, of course, build some dashboards on top or integrate with other BI tools and with the mobile apps and so on. And this is a very common architecture we see more and more, where you build one scalable real-time infrastructure where you consume in real time for some use cases, but also ingest it into other databases and systems for doing the processing there in analytics and leveraging the features of that platform, like you see here in this picture in green with InfluxDB. And so in this case, what we did intentionally, so we didn't use Confluent Cloud because that would already work, right? Because everything is as a service, fully managed. But we built an example on Kubernetes. And this is an example like we see it at Audi, where they have built a template infrastructure because they knew from the beginning they will have to roll it out not just in Europe and in the US on AWS, but also in China on Alibaba, and maybe also in Russia where there is no cloud at all. And so we have built a template where we deploy the MQTT stuff and the event streaming stuff on a Kubernetes cluster so that we can roll it out everywhere the same way. In our demo with Terraform, we use GCP for this. And also we have configured different databases for that. So we use Kafka Connect for that. And so with that, in addition to this real-time analytics platform, you can also ingest the data into a platform to store the data, for example, to do time series analytics. And so if you want to combine this example here with InfluxDB, you just use the connectors for InfluxDB. These are built by Confluent and fully supported 24/7. And this is for source and thing. So you can ingest all the data into InfluxDB for doing real-time analytics and batch analytics there and store the data forever. But also, if you want to, you can also send data back to Kafka. For example, if your real-time analytics in InfluxDB get some interesting insights, then you might send them back to a Kafka topic so that the other applications can consume that again. And again, these applications could be some other real-time consumers, or it's another batch platform, or maybe your data warehouse of your choice. And this is how all these technologies complement each other and work together. It's typically not a question of one or the other, but it's really complementary. And so here are the key takeaways for this session. A digital twin merges the physical and the digital world. I gave you a few examples, so like buildings or connected cars or the hospital. And it's really key to remember that this is not just for industrial IoT, what most people think about and what's probably the most common use case, but this is for everything, for humans, for processes. Anything can have a digital twin so that you can leverage that for simulations, for predictions, without touching the existing thing. And therefore, you have seen that Kafka and InfluxDB is really a cool combination to provide an open and scalable and reliable infrastructure for digital twin. This is very different from the proprietary and monolithic solutions which you can buy in an IoT platform. They typically are a monolithic solution, which is very complex and expensive. And under the hood, often these solutions also combine many different tools and code bases. You don't see this when you use it, but under the hood, you see it and the pain because it's really hard to operate this and to scale this out. And what you have also seen is that event streaming complements IoT platforms on the one side to integrate with machines or devices. And on the other side, also with backend systems and applications and databases. So Kafka is really used so much because it can process high volume at scale in a reliable way, but also because it decouples the different systems from each other. And so you can combine it with a time series database for doing real-time analytics, but also with a batch platform like Hadoop and with other real-time consumers. And then you can also do bidirectional communication between the devices and between the digital twin on the other side. And so this is really a powerful combination, and I can really recommend you to try it out. And also, of course, you can contact me if you have any questions for that. So feel free to connect to me on LinkedIn or on Twitter to stay in touch with me, and also drop me a message if you have any feedback about this talk or any questions. So thanks a lot for listening, and have fun with the other talks about InfluxDB. Goodbye.